US Physics Olympiad, year 2019, USAPHO, final round. Problem A3. Electric slide. Two large parallel plates of area A are placed at x equals 0 and x equals d, which is much less than square root from A, in the semiconductor medium. The plate at x equals 0 is grounded, and the plate at x equals d is at fixed potential negative V0, where V0 greater than 0. Particles of positive charge Q flow between the two plates. You may neglect any dielectric effects of the medium. Part A. For large V0, the velocity of the positive charges is determined by a strong drag force, so that V equal mu E, where E is the local electric field and mu is the charge mobility. Question 1. In the steady state, there is no reason but time-independent density of charges between the two plates. Let the charge density at position x be rho x. Use charge conservation to find the relationship between rho x, Vx and their derivatives. Question 2. Let Vx be the electric potential at x. Derive an expression relating rho x, Vx and their derivatives. Hint: start by using Gauss's law to relate the charge density rho x to the derivative of the electric field Ex. Question 3. Suppose that in the steady state conditions have been established, so Vx is proportional to x power b, where b is an exponent you must find, and the current is non-zero. Derive an expression for the current in terms of V0 and the other given parameters. Solution for problem A3. Part A. Question 1. In the steady state, there is a non-zero but time-independent density of charges between the two plates. Let the charge density at position x be rho. Use charge conservation to find the relationship between rho v and their derivatives. Solution for question 1. Consider the region between x and x plus dx. The charge in this region will be rho a multiplied by dx. And because current everywhere is constant, we have dq over dt equal rho a dx over dt, which is speed v, and this equal to constant. If we divide it by area, we will get current density J, and that's constant. If we take first derivative from this current density, we have this expression, which is 0. So we have correct answers. Either rho v is constant, or v d rho over dx plus rho dv over dx equals 0. These are solutions for question 1 in part A. Question 2. Let V be the electric potential at x. Derive an expression relating rho, V and their derivatives. Hint: start by using Gauss's law to relate the charge density rho to the derivative of the electric field E. Solution for second question. Again, if we take the same slice of our constructor between x and the x plus dx, according to Gauss law, we have jump of electric field dE equal sigma over epsilon 0, which is rho dx over epsilon 0. And from here we have dE over dx equal rho over epsilon 0, or second derivative from potential V by distance dx, that's equal negative rho over epsilon 0. That's the answer for question 2. Question 3 from part A. Suppose that in the steady state, conditions have been established so that V is proportional to x power b, where b is an exponent you must find, and the current is non-zero. Derive an expression for the current in terms of V0 and the other given parameters. Solution for question number 3 from part A. Now let's use results from first and second questions. So we have, this is from the first question, this is from second question, which we also call Poisson's equation, and also from condition that V equal mu E, we have this equation. So from the first equation we can exclude rho and V, and we have finally this differential equation. Now because we know that V x proportional to x power b, and we have conditions that total potential difference is V0, so we have V equal negative V0 multiplied by x over d power b, and we can put this expression in our differential equation. And finally we have this equation to find what is b. We have three roots. Root b equals 0 cannot satisfy to boundary condition. For b equal 1 we have a 0 current, so we have only root b equal 3 over 2. And we have finally potential equal negative V0 multiplied by 3 over d power 3 over 2. And now, using expression for current I equal A rho V, we can express rho from second equation. That's a second derivative from potential V. We can use this formula, and also we can use expression for V, which is this expression. So finally we have V equal this expression, potential equal this expression. V we can find from this formula, which is this expression, and rho we can find from this expression, which is this one. And the current equal A rho V, which is this expression. That's answer for question 3 from part A. Part B. For small V0, the positive charges move by diffusion. The current due to diffusion is given by Fick's law. I equal negative AD multiplied by d rho over dx, where d is the diffusion constant, which you can assume to be described by the Einstein relation d equal mu kBT over q, where T is the temperature of the system. Question I. Assume that in the steady state conditions have been established so that the non-zero steady current flows and the electric potential again satisfies V proportional to x power b prime, where b prime is another exponent you must find. Derive an expression for the current in terms of V0 and then other given parameters. Question B. At roughly what voltage V0 does the system transition from this region to the high voltage region of the previous part? Solution for part B. Question 1. We again have that V equal this expression. And now we can use again Poisson equation. It means that from here we can find that B equal 3 and the current equal this expression. To answer for question 2, we just need to equalize currents from first and the second parts. That will be this equation, and from here V0 equal this expression. So that was a solution for part B.